when it comes to bounds in calculations, it's really important that you actually turn the logic on in your brain. These questions, there's a lot of variation that we can have. So you've got to understand what a bound is, and then you've got to understand how the logic works through in terms of using these things in calculations. So if we just do a little bit of a recap on what the bounds are and how we're going to have a general approach, then we're going to do a whole whack of questions today, because that really is the best way to get that experience for using bounds in calculations. So a reminder that when we take a measurement of anything, we never really as accurate as we wish we would like to be. Okay, there's always that idea of we could be either side of the exact line on the ruler, for example. So if our ruler only marks every centimeters, we're not necessarily on the centimeter line. So what we're saying is that depending on the scale we're using, we can only measure really accurately to about half those big units. So what we would need then is to, let's actually draw this one out. So here's our ruler. And we are measuring, but this is one of those rulers that only has centimeters on. So if you were measuring something that was this long, then it's easy. There's 1, 2, 3, this is 4 centimeters. But if we were measuring something else, let's say this line, now how long is that line? Is that line 5, 6, or 7? That's where the bounds comes in. So what we're saying is that anything basically from 5.5 to 6.5, we would call 6. Anything from 6.5 to 7.5, we would call 7. So we can, if we're measuring to the nearest centimeter, we could go half a centimeter up or down and still call it that centimeter. So if we put this into something a little bit more fancy, what we would say is that our lower bound is less than or equal to our measurement with units, which is less than our upper bound. Because we've got to bring in our ideas of inequalities and rounding here as well. So if we look at our orange line, okay, so it is length in centimeters that we're dealing with. So the lower bound would be 5.5. Okay, halfway between 5 and 6, less than or equal to length. Less than the upper bound would be 6.5. So we have our nice and neat 5 up, 5 down, but our inequalities are so important here because 5.5, if you rounded 5.5, it would go to 6. And 6 is the one we're working with. If you rounded 6.5, it would actually go to 7 to the nearest centimeter. But 6.4999999 to the nearest centimeter would round to 6. So that is why we include the lower bound, but we exclude the upper bound. So 5.5 to 6.5 would be our 6. If we want to formalize this a little bit more, what if we were measuring kilometers, or if we were measuring grams, or if we were measuring time? Okay, everything is measured with a bound because everything is measured with a level of accuracy, and that is your key. We would have a measurement that is made to the nearest something. So in our case here with our orange line, it would be the nearest centimeter. It could be the nearest millimeter, it could be the nearest kilogram, it could be the nearest second, it could be the nearest hour, okay? But we've got this phrase in our question that says to the nearest something. And that something is a really important piece because in order to calculate our upper and our lower bound, we take this nearest something and we go plus or minus half the nearest. So plus or minus half a centimeter got us our 5.5 and our 6.5. If we were measuring to the nearest hour, we'd be going plus minus half an hour. Okay, so we're always getting that plus minus half of our nearest measurement. When it comes to actually working with the bounds and calculations, the first thing you've got to do when you read the question is that you've got to state the bounds for any measurements in the question. You've got to know what it is you're dealing with. So have a careful look at the phrasing of the question. We're measuring to the nearest what? And then you can go plus minus half of that. Now, once you've got those, you're going to actually stop and think. How are the values combined? For the calculation that you're doing. So first we're going to state the bounds, then we're going to think, and then only we're going to calculate. So as I said, the best way to work on these is practice. So the more different situations you work with as you do questions, the more different ways you'll see how this is done. So what we're going to do now is go and actually do some past paper questions so that you see some variation in what we have in terms of these bounds and calculations. So we have a collection of past paper questions. Get them to something where it's comfortable to write on. Okay, so starting out with the first one from winter 2016. The sides of a square are 8 centimeters. Correct to the nearest centimeter. See, here it is already. So we're going plus minus 0.5 centimeters. Calculate the upper bound for the area of the square. So the first thing we're going to do is state the bounds for the measurement in the question. So we have here side in centimeters. Greater than or equal to and less than. So the side of the square is 8, the nearest centimeter, so plus or minus 0.5. So 8 minus 0.5 gives us 7.5. 8 plus 0.5 gives us 8.5. So now we have to think, calculate the upper bound for the area of the square. How would we get the biggest area? The biggest area would come from the biggest sides. So, upper for area equals 8.5, and it's a square, so it's just 8.5 times 8.5, which gives us 72.25. So our answer, we don't round these ones. We leave these ones nice and exact because we're working now with bounds. It's working with a little bit more accuracy and understanding of that situation than our normal questions. So we don't want to round these to 3 significant figures. So we read our question, got our up and downs, wrote out, thought about it, and calculated. That's what we're going to do for each and every one of these questions. So, next question. The length of a car is 4.2 meters. Correct to 1 decimal place. Write down the upper bound and the lower bound of the length of this car. Correct to 1 decimal place. Well, how do we write 1 decimal place? We would write 0.1. Because there is our 1 decimal place. So therefore, we are going up and down half of 0.1. So 0.05. So our upper bound would be 4.2 plus 0.05. It's 4.25. Our lower bound would be 4.2 minus 0.05, so it would be 4.15. So this question didn't actually have a calculation associated with it. It was just a stating of the bounds, but this use of the 1 decimal place is slightly unusual. Most of the questions do to the nearest something in terms of units rather than decimal places. So I just wanted to add this one in, so we've got a little bit of a sight of when it happens with decimal places. This is the sort of thing that we're working with. So moving then to summer 2017. One lap of a racetrack measures 3,720 meters. Correct to the nearest 10 meters. So half of this plus minus 5 meters. A car completed the lap in 75 seconds. Correct to the nearest second. So we're going plus minus 0.5 seconds. Calculate the upper bound for the average speed of this car. Give your answers in kilometers per hour. So we're going to have to be doing some conversions here. So for those of us who like to see it, we have distance, speed, and time. So in order to do speed, we need distance over time. So now let's do some. First off, stating bounds. So if we work with the distance in meters, because that's what's in our question. Now I'm setting up our bounds. So 3720 minus 5 gives us 3715. 3720 plus 5, 3725. Now they want your final answer in kilometers per hour. I actually prefer not to convert it at this stage. Okay, so if it was in meters, to put it into kilometers, we divide by 1,000. 3.715 less than or equal to distance in kilometers less than 3.725. Okay, so then we do the same thing for our other measurement, because we do this for all our measurements. We're now looking at the time. So time in seconds, our bounds 75 minus 0.5, so 74.5. 75 plus 0.5, 75.5. But again, we want hours. So 1 hour, if we think about it, is 60 minutes. Each minute is 60 seconds. So 1 hour is 3,600 seconds. That's a lot of seconds in an hour. So now we're going to convert our time in seconds to time in hours. So 74.5 divided by 3,600, that gives us 149 over 7200. 75.5 divided by 3,600, that comes out to 151 over 7,200. So upper for speed. How would we get the greatest speed out of this? We would want to be looking at the longest distance in the shortest time. So our longest distance is 3.725 kilometers. Our shortest time, because that would be the greatest speed to get that distance, 149 divided by 7,200. So we're going to flip in times and do it all on the calculator, because we're dealing with some quite interesting numbers. And we come out to, very straightforward and simple, 180 kilometers per hour. So this is what I mean by the fact that you have to sort of sit and think through, what's the logic behind getting my greatest speed? Is it the shortest time in the shortest speed, or the longest, shortest time and shortest distance, longest time and longest distance, or is it combining the two? Okay, so in this case, we wanted that longest distance in the shortest time to get the highest speed. So moving on to something again, where you ought to be awake. A metal pole is 500 centimeters long, correct to the nearest centimeter. So this one is plus minus 0.5 centimeters. The pole is cut into rods, each of length 5.8 centimeters, correct to the nearest millimeter. We've changed units. So this means that we're going to go plus minus how much of a centimeter? Well, a millimeter would be 0.1 centimeters. Because there's 10 millimeters in 1 centimeter. So half of the 0.1 means we're going plus minus 0.05 centimeters. And now we're very clever because we've got everything into 1 unit. So then calculate the largest number of rods that the pole can be cut into. So first off, we're going to state those bounds. So we have the pole in centimeters. 500 minus 0.5, 499.5. 500 plus 0.5, 500.5. Then we have the rods, and they're also in centimeters, because we were organized when we read this question. 5.8 minus 0.05, 5.8 plus 0.05. Now we have to stop and think. The largest number of rods. Well, to get lots of rods, we need lots of little rods. So we want that shortest length for our rods. But to get lots of rods, we would want the longest pole possible, because then we can cut it into more rods. So longest pole, 500.5, divided by shortest rods, 5.75, equals 87.04. Now we've got to think, because in this case, rounding to 3 significant figures would be 87.0. But we can't cut a piece of a rod. Well, we can cut a piece of a rod, right? But we want to know the number of rods. How many actual full whole rods? So the answer is just 87. 87 whole rods. That's the largest number of rods that you can cut from this pole. The next question. The house, so this is carrying on from previous parts of the question, is built on a rectangular plot of land, 21 meters by 17 meters, both correct to the nearest meter, plus minus 0.5 meters. Calculate the upper bound for the area of the plot. So, our plot is 21 by 17. We're going to need both of these measurements put into bounds. So we have length in meters, 21 minus 0.5, 21 plus 0.5. And we have width in meters, 17 minus 0.5, 17 plus 0.5. And they've asked us for the upper bound for area. And now you start to see why it's good to do lots of questions. Because the very first question we did was also similar to this. Upper bound for the area of the square. So to get the biggest area, we need the biggest lengths. 21.5 times 17.5, and that gives us 376.25. So the upper bound for the area of this plot is 376.25 meters squared. We've got a few more questions lined up. We'll see how many of them we get through before the end of the lesson. Next one from May, June 2017. A rectangle has length 62 millimeters and width 47 millimeters. Both correct to the nearest millimeter, so plus minus 0.5 millimeters. The area of this rectangle is a millimeter squared. Complete the statement about the value of A. So A and C here are inequalities. So we now need the lower bound and the upper bound for the area of this rectangle. So we start the same way as we always do. We have length in millimeters. 62 minus 0.5, 61.5. 62 plus 0.5, 62.5. Then we have width, also in millimeters. 47 minus 0.5, 46.5. 47 plus 0.5, 47.5. So now we need to do the lower bound and the upper bound for the area. So the lower for area, how do we make the smallest area? Well, we take the smallest length of it. So 61.5 times 46.5. So our lowest for area comes to 2859.75. Our upper for area would be, again, our two biggest values. So 62.5 times 47.5, giving us 2968.75. So if we put our bounds in their places in the question, in the answer, 2859.75 to 968.75. And what's really cool is if you combine different numbers from these four numbers here, you wouldn't be able to get a smaller value or a bigger value for the area of this rectangle. Because when you take the two smallest, you get the smallest. When you take the two biggest, you get the biggest. So the last question, in 2016, a company sold 9,600 cars, correct to the nearest 100. So here we're going plus minus 50, half of 100. Write down the lower bound for the number of cars sold. Lower bound, 9,600 minus 50, so 9,550. The average profit on each car sold was 2,430, connect to the nearest $10, plus minus $5. Calculate the lower bound for the total profit. Write down the exact answer. So, we're going to do this one slightly different because now you had a bit of practice. Lower bound for the total profit. You know this one would be fewest cars times smallest amount. Now they've talked us through the fewest cars already. The lower bound is 9,550. So our lower bound for the cars equals 9,550. Our lower bound for profit is 2,425 per car. So lower for total equals 9,550 times 2,425, which is 2,315,875 $. That is an awful lot of money. So when it comes to bounds, practice, 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 and you'll start to see that they're not quite as weird as they look out at the beginning.